Hello, everyone. My name is Akshat, and welcome to the next episode of Math Challenge Monday. So today we're going to be looking at the formula for the area of a circle, which is pi r squared. And most of you know the formula for the area of a circle, but today we're going to be doing something a little bit different, and that's going to be deriving the area of a circle formula using calculus. So if you have some knowledge of calculus and integration, I encourage you to try this problem out on your own. But if you want to see the solution or you're just curious, you can follow along here. So I've written the general equation for what a circle represents, which is x squared plus y squared equals r squared. So if we're going to manipulate this in any way, it'll be helpful to get this in terms of y equals some function of x. So let's subtract x squared from both sides. So we have y squared equals r squared minus x squared. And now if we want to isolate y, we just have to take the square root of both sides. So we get y equals the square root of r squared minus x squared. But now we have to remember that since we took the square root, we can have a positive and a negative version of those two functions, because a negative squared will get you a positive. And this should make sense if we look at the circle over here. This top half would be the positive square root of r squared minus x squared, and this bottom part would be the negative part of the square root of r squared minus x squared. So if I wanted to use calculus, I would say, okay, I have a top and a bottom function. I can take the area between the top and bottom function just like this and integrate it between two bounds. But there's actually an easier way to do this. I know that my area of the circle is separated into 4 equal parts. And it's not exactly drawn to scale here, but just imagine that it's drawn exactly equally to 4 parts. So if I take the area from just this section, this piece right here, then if I multiply it by 4, I should have the entire area of the circle, and it'll be a lot easier to compute that way. So let's go ahead and do that. So I'm going to write 4 because I'm multiplying whatever area I have by 4. And then we'll have the integral here. Now, what are my bounds? So I'm starting at 0 here, if we're taking this to be the origin. And my radius is right out here at r, so we'll just call this r. So the lower bound is 0, upper bound is r, and we're using the positive side of that square root of r squared minus x squared. So we'll write that accordingly. R squared minus x squared. And we're integrating with respect to x right now, so we'll put dx. Now, if you were to evaluate this integral all by itself, it's actually pretty messy, and there's no real good way to do it with antiderivatives. So what we're going to have to do is a trig substitution. So if I let x equal to r sine theta d theta, and if I take the derivative of this now, so dx equals r cosine theta d theta, then we can substitute whatever we have in here back into here. So there's actually 3 things we're going to need to change when we make this substitution. One is the bounds, right? We're not integrating this with respect to x anymore, it's with respect to theta. So the bounds also have to change. The actual equation, as you might have guessed, needs to change because the x is being replaced with the theta. And the dx, we're not integrating with respect to x again, we're integrating with respect to theta. So the dx needs to turn to d theta. And luckily, we've already done all the work required, so we just need to figure out what the bounds are. So how do we do that? Well, if we look at our original equation, x equals r sine theta, we can plug in our 0 and r to find our bounds. So if we plug in 0 for x, we get 0 equals r sine theta. If we divide by r, then it's sine theta equals 0, which means theta equals 0. So we know that the bottom is going to stay at 0. Okay, fair enough. What about r? If we plug in r for x, we get r equals r sine theta. If we divide both sides by r, we'll get sine of theta equals 1. Now that would equal pi over 2, right? Sine of theta equals 1 at pi over 2. And that should make sense if you remember the unit circle at all. The pi over 2 was always at 90 degrees above the origin, or 0 degrees. So now we have our new bounds, and the 4 is going to stay the same. So I'm going to put it right there. Pi over 2 over 0. Now, in terms of changing the actual equation, we have r squared minus x squared. So we'll put the r squared as the same. Then we know that x is r sine theta. So if we just square it, we'll get r squared sine squared theta. And we're not quite done. We have to substitute that dx again. So we'll multiply this by r cosine theta d theta. Now everything is in terms of theta, which is exactly what we wanted, and it'll make this easier to solve. You'll notice in here we have an r squared common, so we can factor that out. So I'll write that again. R squared times 1 minus sine squared theta times r cosine theta d theta. And if you remember one of your trig identities, 1 minus sine squared is actually equal to cosine squared. So just like that, we've simplified this integral even more, and you can probably see where this is starting to go, but I'll write it out. So 4 pi over 2 times the square root of r squared cosine squared theta d theta, and then times that r cosine theta again, and then d theta. So if we take the square root of r squared cosine squared, we're just going to get r cosine theta, but then we're multiplying it again by this r cosine theta. So ultimately, when we evaluate this part of the expression here, we'll get 4 times the integral 0 pi over 2 times r squared cosine squared theta d theta. All right, so we've actually simplified this quite a bit, but there's still some more work left to be done. So this r squared is technically a constant, right? It could be any number. It's not a variable because we're integrating with respect to theta. So this r squared is treated as a constant, which means I can bring this out here and rewrite this as 4r squared times the integral 0 pi over 2 of cosine squared theta d theta. And now there's actually another useful trig identity formula that we can utilize here. And that's that cosine squared theta is equal to 1 plus cosine of 2 theta over 2. So let's go on to the next page, and then we will rewrite this. So we have 4r squared times the integral of 0 to pi over 2 of 1 plus cosine 2 theta over 2. Now, if you think about it, there's a 1/2 over here. So this would be like saying 1/2 times 1 plus cosine 2 theta. So we can actually bring this 1/2 again out because it is a constant. If we bring in this 1/2 out, it would be like saying 1/2 times the 4r squared, which would make it 2r squared. So we will rewrite this again, saying this is 2r squared times the integral 0 pi over 2, 1 plus cosine 2 theta. And there's no divide by 2 because we already took that 1/2 out. So now if we use our regular antiderivative and reverse power rule traditional rules, we can actually evaluate this integral as it is. We've done all the legwork necessary. So let's go ahead and do that. I'm going to leave the 2r squared out, and we'll put in brackets here, integrating that indicating that we're integrating this now. So if I integrate 1, that's just going to be theta, right? Because if I integrate any constant that's 1, you just get the variable itself. In this case, that's theta. And then cosine 2 theta. So the antiderivative of cosine is sine, but because we have that 2 theta, we need to divide by 2 again, and that would be the reverse power rule. So make sure you review that if you need help with that. but you would get 1/2 sine of 2 theta here. And of course, the bounds are pi over 2 and 0. So we are pretty close to finding our answer here. So let's leave 2r squared out again and put the brackets. And now let's evaluate this at pi over 2 and 0. So pi over 2, I can just plug in for theta, no problem. Pi over 2 plus sine of 2 theta. So 2 times pi over 2 is pi, right? Because the 2's will cancel out. So you'll get 1/2 sine of pi minus, so now we're going to move on to the lower bound here. Plug in 0 for theta, you just get 0, plus sine of 2 theta, which is just 1/2 times sine of 0, right? Because 2 times 0 would get you 0. All right, now we can simplify this. So I'm going to write the 2r squared again. Let's simplify inside the brackets. So sine of pi is actually 0. If you remember your unit circle, it's at 180 degrees. So 1/2 times 0 is just 0. So we have pi over 2, just pi over 2 for this side. And sine of 0, just like sine of pi, is also 0. And this is 0 plus 0. So we're actually subtracting from 0. So in total, you get 2r squared times pi over 2. And if you cancel out the 2's here, because of the top and bottom, your final answer is pi r squared. So it's a pretty neat thing. And just like that, we've derived the formula for an area of a circle by integrating the area of a circle and separating it into 4 equal parts to make our job easier. And with some trig identities, we were able to solve this problem.